Hello everyone, I'm going to make a couple of videos on work problems where we're lifting, and we're going to be doing one where we're lifting with cables or ropes and a separate video where we're lifting or pumping liquids. So here's the scenario, and I made um, these figures here with the help of some AI. Used Copilot to help create some of these, just modifying some images I found other places online. But we're going to have this scenario where we're going to have something, possibly either just the cable or rope or something attached to it, and we're going to be lifting it through a certain length. Right? In this picture, we're going to be lifting it a height of H units. And what we're going to think about doing is the work done. We got to be, and I have this written out a little bit below. Consider when we split this interval up, and it's often convenient for us to draw our x-axis going vertical here. Right, so we're going to think about this as the x-axis going up, right, and this on the ground here is going to be x equals 0, and we're going to be partitioning this interval up using a regular partition. But we want to think about looking at the kth subinterval, right? How long or how much work does it take to bring the bottom of the cable and whatever else is attached to it through the k subinterval? Right, so we're going to be splitting it up like this. The width of the k subinterval is going to be delta x, and the work done is going to be, we got our rope here hanging down with whatever objects attached. We need to know how much work it takes to take the bottom of the rope and everything else above it and all the cable that's out through the k subinterval. And this is all connected, so when we pull the object or just the cable or rope through the k subinterval, everything is pulled up at once. All right, and there's a difference between these types of problems when we go through the setup. All right, when we go through the setup, as we're going to see in a minute, we're always going to have a sum of estimating the work done on the k subinterval, right, and splitting that up into n equal pieces, and that's going to be force times distance, right? But when we do the lifting liquids problems versus the lifting with cables or ropes, the setup is a little bit different, and that's what we're going to explain across these couple videos. All right, so we got to understand the process because there's slight variance from problem to problem. But we're going to have some commonality that we're going to usually draw our x-axis, not every time, but most of the time, going upwards here, where x equals 0 is the bottom is how I prefer to do it, whatever height you're given in your problem. All right, some things we got to watch out for is when we're setting up problems involving cables or ropes, maybe have something attached, maybe not. We got to take into consideration the cable is connected, and when we pull it up, when it's pulled up, the entire portion hanging is lifted. We can't layer it out like we can with pumping or lifting liquids. All right, so what we have to think about then is partitioning that the distance that the cable is moved into those segments as we did in the picture above, and think about the work required to move the bottom of the cable through the kth slice of distance. Let's go back up to the picture. This is going to be our kth slice of distance. How can we get the bottom through that amount of distance, which is going to be delta x? Okay. Well, that's going to be, as we said there, d sub k is going to be delta x. F sub k, the force required to move through the k slice of distance, is going to just be the weight. Right? It's the force required to overcome gravity. So it's the weight of the length of the cable that's out there plus any other objects. So it's going to be the weight of the rope or cable plus the weight of other objects. This is just a note, but if we're given a lot of times we're going to be in these problems given the linear weight density. So we're going to take that linear weight density and multiply it by the length of hanging cable, and that will depend on how much cable is out, and therefore that's going to depend on x. Right, so we're going to see for these problems the delta x is going to be always the distance. It's going to show up in the same place all the time. The force is going to be what's going to vary. Right, and then as we add things up and take limits as n goes to infinity, we're going to get a definite integral out of this, and we're going to be integrating a force function. All right. Now, a couple other notes here before we get to the example. The units of work that we're going to be seeing are either going to be, if we're in the metric system, Newton meters, which is what's called joules, or foot pounds if we're in the imperial system. Right, when we go through these setups, we'll just make sure that the units are working out correctly in the Riemann sum, and therefore it'll work out correctly in the limit in the end. Here's our example for this recording. how much work is done lifting an injured child who weighs 60 pounds to the top of a 15-foot hole using a stretcher weighing 10 pounds and a cable which weighs 2 pounds per foot. So that's what we're talking about when we think about the weight density, 2 pounds per foot. All right, so here's just a picture about how we're going to set this thing up. So we have this height is going to be 15 feet. Again, we're going to think about the bottom of this being x equals 0. The top is going to be, in this case, 15 feet. We want to think about partitioning this, and then what does it take to get the cable and the object, in this case, it's the child and the stretcher, through that k subinterval. All right, so where we're going from x of k minus 1 is the lower end point of it to x of k. Again, this distance here is going to be delta x in the figure there. All right, so that's what we got to write down in terms of our Riemann sum. So I'm just copying, repeating some of the things we had up there before. Again, we have delta x is the distance we're going to move the bottom of the cable. It's how far it's moved through that k subinterval. We got to work on the force required to move it through that k subinterval, which is going to be the weight. All right, so that force is shown at the bottom here. The weight of the child, the total weight lifted would be the weight of the child plus the weight of the stretcher plus the weight of the cable. We're given in the problem that the weight of the child was 60, so we're just going to substitute in 60 here. The stretcher was 10. The weight of the cable, we got to know how much is out. So let's go back up to the figure to think about that. Well, the amount of cable that's out is going to be, oops, the amount that is out is this vertical length right here, which in this problem is going to be, we're going to just estimate that by 15 is the top of it is x equals 15 minus x sub k. Let's just go to the top of that. I kind of drew it kind of somewhere in the middle, but we can estimate with that. That is going to be how much rope we have out, right? And so we go down to plug that in. The weight density, we were told it's 2 pounds per foot, right? And then in this case, the length of the cable out for us is going to be 15 minus x sub k. All right, so we're going to multiply those together and notice that this is in feet, right? And the units do work out well. In this case, feet times foot pounds is going to give us pounds, which are going to be the units for force. So the total overall unit here is going to be pounds. Okay, so now we need to go through and write out what the Riemann sum is going to be. And we're in pretty good shape here because we've got the force. We know from before it was going to be F sub k times delta x. All right, so we're going to write out our sum next. So the work done is going to be approximately the sum of the individual works done over each subinterval. And that's force times distance. All right, and this is going to equal, let's say approximately equal to, we're making some approximations here that will get better and better as we increase the number of subintervals used. But that is going to be our force function as indicated up here is going to be 60 plus 10 plus 2 times 15 minus x of k, and all of that is times delta x. All right, let's just clean that up a little bit and then combine like terms. So this sum is going to turn into, we get 70 plus distributing the 2 through. So continuing just to combine this up, we're going to have 70 plus 30 minus 2x of k times delta x. And therefore we have 100, just adding like terms again, minus 2x sub k times delta x. All right, now as n is approaching infinity, this is going to turn into a definite integral. All right, we're going to get the exact work done. So these approximations are going to turn into exact statements. So the overall work done is going to be the integral, in this case, from 0 to 15. And we want to lift the child at everything from the bottom of the hole, which in this case we conveniently put as x equals 0, to the top and out, which is 15 feet high. Our integrand becomes 100 minus 2x, not x sub k. Delta x turns into dx. And we got a pretty straightforward integral to work out. Okay, so we'll just finish that off to finalize this example. So our antiderivative, we're going to have 100 x minus x squared. Evaluate this by plugging in 15, plugging in 0, subtracting. This can, what do we get here? So 100 times 15 minus 15 squared. And that can be computed, calculated out to 1,275. Again, the units on here are going to be foot-pounds. Right, foot-pounds. The units did match up inside of our Riemann sum. I just want to go and point that out. All right. So getting the integral, getting the Riemann sum set up is the key to these problems. All right, and then it's usually going to be a pretty straightforward evaluation of the integral at that point. But I just want to make the point that the units do work themselves out, as we had said above, that the force was totally in pounds already. All right, so the force function was in pounds. Delta x, the units on delta x, that's feet. So we get pounds times feet, which is foot-pounds. We usually call it foot-pounds, not pounds-foot. All right, so we get pounds times feet here. All right, so our units work themselves out. And that's just kind of the general setup, as a discussion of the general setup, and then the specific example that we worked out here. So one thing, again, just to emphasize, we need to keep in mind here that the force is going to, for these lifting with cables or ropes, the force is going to represent the weight lifted. All right, and that's going to vary on a problem-by-problem basis, but d sub k is going to be delta x all of the time for these types of problems.